Greetings, friends of astrobiology, and welcome to Ask an Astrobiologist, the show that celebrates the science and the scientists in the quest to understand the nature of life. I'm Graham Lau, your host for this month. I also go by the Cosmobiologist on Twitter and on Instagram. You can find me online. And our show is brought to you by SegaNet.org and the NASA Astrobiology program. As usual, we're really excited to have you here to ask questions that you have about astrobiology, about careers, about research, and about the lives of scientists involved in astrobiology. I'm really excited for the guest we're going to have on for this episode, but we have a few of our housekeeping things here to do first. First off, as many of our longtime viewers know, we have our monthly background quiz, where every month there's a really awesome picture behind me, and it's your job before the next episode, within one day before the next episode, we announce on Twitter, on SegaNet, at SegaNorg, the background quiz, so you can guess what this image is. The winner always gets a few of our NASA astrobiology graphic histories, created by the artist and scientist Aaron Gronstal, who was a past guest on our show. You also get some NASA stickers. So this past month, the image is coming up now. This picture is an image that was taken from CERN, located in Switzerland, between Switzerland and France, at the Large Hadron Collider. Now, I know some folks are wondering, what does the Large Hadron Collider, what does CERN have to do with astrobiology? But remember, there's more to astrobiology than just biology, just studying life on Earth or listening for messages from ET. There's a lot more, including understanding consciousness. What is the self? What is the universe? What is matter? Where do we come from? And those questions, they touch in all realms of scientific understanding, including in cosmology. And as I'll tell you here in a minute, that background also has to do with this month's guests. But for right now, let's just say that our winner for this past month was Denise at AKBLT_DNZ on Twitter. Denise will win our prizes, so congratulations for guessing the correct background there with the Large Hadron Collider. Also, as you know, every month we announce an Ambassador of the Month. Some person or group who, through Twitter and Instagram, Facebook, LinkedIn, Reddit, all the various social media channels, is out there promoting our show, talking to their friends, sharing information about our guest, asking questions before the show. And this month, our Ambassador of the Month is a group that I'm actually a part of called the Explainables. The Explainables is a science communication and tech communication startup group that was actually founded by this month's guests. And I'm proud now to be an associate of the Explainables, trying to find better, richer ways to communicate our science, communicate our knowledge with the larger world, and to teach other scientists and other researchers how to communicate as well. So with that, it's a good segue into this month's guests. So just like the Large Hadron Collider is located in Switzerland, this month's guest is coming to us from Switzerland, from Bern. His name is Daniel Angerhausen. He's a longtime friend of mine, and like I said, a founder of the Explainables. He's been a mentor for the NASA Frontier Development Lab, and as we're going to find out, he has a lot of really awesome background in astrobiology during this episode. So, Daniel, thanks for joining us for Ask an Astrobiologist.
Hi, everyone, and good evening from Switzerland.
Yeah, so it's kind of always fun having, a little bit of a time change, since we're talking across the planet. It's so cool that we can do that. You and I have known each other for some time now through science communication, and I definitely want to talk about the Explainables, about communicating science. But this is Ask an Astrobiologist, and so to prepare all of our audience for asking questions of you about your research, I wonder if you can start off by giving us some of your background and maybe even tell us what inspired you to get involved in astrobiology.
So I'm by training an astrophysicist. So I did my undergrad in physics in Germany, back in Cologne, Germany. And when I've finished my studies, I had to choose a special topic. So you either do astrophysics or nuclear physics or theoretical physics. And I figured that if I do theoretical physics, I'd be standing at a blackboard for the rest of my life. If I do nuclear physics, I'd probably be sitting in the basement of a reactor for the rest of my life. But as an astrophysicist, you might at least once in a while, go to Chile or go to Hawaii to see the great telescopes and observe with them. So actually one of the reasons to then specialize in astrophysics rather than another sort of physics was actually to travel. And then my topic, so exoplanets, looking for stars, extrasolar planets, looking for planets around other stars, was actually chosen because I lost the bet. So maybe we can, get to the story a little bit later. But then I chose exoplanets as my topic, and that was immediately connection to astrobiology. So as you probably have heard in this show a couple of times, there are these big two approaches looking for life in our solar system. With probes and rovers, we might even be able to get on these bodies in our solar system. And the other, somewhat competing way to find life in space is on planets around other systems. And that's where my background comes from. And I really love to be involved in the astrobiology community because it's a much cooler community than the astronomers, if I can say that on the show. So yes, that's how I got into it. So
that's great. And we're totally happy to have you call astrobiologist the coolest. Nothing wrong with that. I do want to hear about that bet. But before we get there, I wonder if you could just tell the audience what you do in your day-to-day research then for trying to understand exoplanets and how that really comes into the realm of astrobiology.
Mm-hmm. So in the past, I was involved a lot in observing. So in even my undergrad, I already started to do exoplanet observations. Some of you might have heard about transit observations, the observations that Kepler does, that the Spitzer Space Telescope does from the ground. So I was really ambitious as a young student, trying to do these amazing observations we got from space, also from the ground. So I was quite lucky to win time at the Very Large Telescope in Chile, at the Keck Telescope in Hawaii, to try these observations also from ground-based telescopes, and it didn't really work out. So the lesson that we learned was that kind of stuff doesn't really work from the ground. So then the next step was to go on a plane, and we might talk about SOFIA later also, how you can do observations actually from a plane, which is somewhere between the ground and space. So that was mostly that observational background, so trying to find new methods, trying to find new telescopes, new instruments that one could use to observe these exoplanets. And then I got more and more involved in astrobiology, also looking at what are these spectral signatures, these so-called biomarkers that we one day want to observe in these exoplanets, and also looking at what kind of missions, what kind of satellites, maybe even a telescope on a balloon, on a plane, we could build to observe these exoplanets. Yeah, so this is my main background, thinking about new methods and new instruments, new missions, how we can observe these biomarkers, hopefully within my lifetime. So.
That's awesome. Before we talk about SOFIA, and I definitely want to talk about SOFIA and what it's like flying on an airplane with a giant door hanging open to telescope. Just before we get to that, I myself, I've been to the Very Large Array in Socorro, New Mexico, and I've traveled a bit. I've seen Mauna Kea as a tourist. I had a chance not to use the telescopes, but to see Keck. I wonder if you can explain for the audience what it's like for you as a scientist and just as a human being, having a chance to see these large observing installations on the planet.
So for me, it was, first of all, a very personal experience. So it was, as I mentioned, really early. I think I just finished my undergrad or finished up my diploma thesis back in Germany. And it was really the first time I used a telescope. It's kind of crazy. My first telescope was a 10-meter Keck telescope. So and then you drive up the mountain. It's really surreal because people who've been to Big Island, Hawaii, maybe know that I heard like all the climate zones of the Earth are somewhere on. It might be a little bit exaggerated, but there's really, really diversity of, desert and tropical rainforest. And then you drive up the mountain, and then you eventually are in the snow, and then standing on top of Mauna Kea, around you just ocean, you're above the clouds. And that was really like a moment for me where I realized, okay, this is why I spent like the last 3 years in the library, learning for my exams. So this was really like a rewarding moment for me. And it's also a very holy place. So maybe in the rest of the show, we might also come to this, big discussion nowadays, is it the right place to put a telescope? So I was also very aware of that, that it was a holy place for the First Nations of Hawaii. So it was a very inspiring moment and an inspiring place for me, still is.
That's wonderful. Yeah, and you're more than welcome to talk about what's going on right now with TMT. If you'd like to explain to the audience what's happening. I'm sure some of our members of the audience do know what's going on right now, but if you'd like to just give us a quick background, I'm sure they'd love to hear it.
So the short story is that the Mauna Kea is one of the most holy places for the First Nations of Hawaii. And there's a big discussion about building the next big telescope there, the 30-meter telescope. And there were protests where locals were hindering people to go up there and do the observations. And I don't want to go too deep in this discussion. I mean, it was just look up on hashtag TMT on Twitter to get a picture of it. There's very extreme positions. There's some, more moderate positions, and it's a long story. And I think it's also something that we need the social sciences for. So I think this is also one of the questions that I saw on Twitter, where can social sciences help astrobiology, astronomy? I think this is exactly one of these fields, or one of these discussions where we really need input from the social sciences, how to communicate better with each other, how to communicate with the communities to solve these problems.
Oh, absolutely. I definitely agree with that. And I know the exact question that you're thinking of, and we'll definitely get to that question then. That comes from the president, CEO of the Sociology Research Institute. And it is important to consider the social sciences, how they impact our research, our observing. So let's go to SOFIA now for a little bit. I'm sure many of our audience have heard of SOFIA, this giant modified 747 where they have a telescope sticking out a giant door. But you've actually flown several times on SOFIA and have used that telescope for observation for doing your research. I wonder if you can speak to the experience and to all of the research going on using this giant telescope on a jet.
Yeah, so SOFIA stands for, we love our acronym. So SOFIA stands for Stratospheric Observatory for Infrared Astronomy. So pretty smart acronym, but it's even better. It also works in German. So it's the Stratosphärenobservatorium für Infrarotastronomie. So, and this is because it's a collaboration of NASA and the German Space Agency. So it's an 80-20 deal between these two space agencies that built that telescope about 10, 15 years ago. It's, as the name says, an infrared telescope. So the main reason we need to get high, as I call it in some of my outreach talks as astronomers, why we build telescopes on mountains or even telescopes on satellites, is that some of the light we want to observe doesn't really penetrate the atmosphere right to the ground. So the only really part of the spectrum that we can see from the ground is the optical light and the radio. This is why we have optical telescopes and radio telescopes. This is why our eyes and our phones work in the radio and the optical. Everything else gets absorbed somewhere in the atmosphere. So most of you might know the UV layer, the ozone layer is absorbing the UV light. So if I'm a UV astronomer, I really have to build a satellite that goes above the ozone layer. And there are certain wavelengths in the infrared who penetrate the atmosphere about the height of the stratosphere. So if you go above most of the water, which is below the stratosphere, below the tropopause, if you fly high enough, slightly higher than commercial airplanes, you're basically in an environment which is similar to space in terms of, the infrared radiation that you get. And this is the reason why SOFIA was built. So you build a telescope on a plane, go as far up in the atmosphere to the place where you can see the infrared light, and then basically have a space telescope that comes home every morning.
That's awesome. It's kind of a cool idea, right? Because it costs a lot of money to put telescopes into space. And then the idea of servicing them, Hubble was serviceable. We serviced Hubble 4 times, but newer telescopes like the James Webb Space Telescope, they won't be serviceable. And so we built these multi-billion-dollar telescopes. But then with SOFIA, we have kind of the happy medium, right? This in between where we get to fly high above all that water, but we're not spending multi-billions of dollars on something we can't fix if it breaks.
I mean, SOFIA wasn't like super cheap. So I think if you break it down in costs per observation hours, it's in the same ballpark as the Great Telescope, as Hubble or James Webb. But it's a really unique wavelengths region. So it covers really the mid-infrared and the parts of the radio spectrum that you can't really get from any other platform. So that's why it's really unique. And as you said, it's really it's really about the servicing, right? So you mentioned these super dangerous and expensive missions, for example, to replace instruments in the Hubble Space Telescope. And one has to keep in mind, if telescopes like James Webb are flying, the instruments on board are 10, 15-year-old technology. Right, so when James Webb launches in 2 years, fingers crossed, or in a year, it will have cameras in space that are technology from a decade ago. Whereas SOFIA has a call for new instruments every other year or every 2 years, so that you can really put your newest camera, your coolest, newest infrared detector that just got out of the lab on SOFIA and bring it immediately in a space-based environment. So this is really the main advantage of SOFIA, to have this super quick turnaround of instruments in that environment.
That's awesome. I wasn't aware that it actually cost about the same for observing, but yeah, I mean, just servicing it and adding new instruments is really incredible. And I'm glad that you pointed out to everyone, sometimes we forget that getting things into space is not easy. Space is hard. And to get things that are flight worthy, it can take time. And so these telescopes, when they go up, they're using old hardware, old software. I mean, the Galileo spacecraft, when it went to the Jovian system, had very old cameras on it. They had so much extra film just for those cameras because they weren't used to more digital cameras at that point on spacecraft yet. Before we go into the next topic I'd love to talk about with you, Daniel, I do want to remind our audience that you can always ask questions for Daniel right now on seganet.org in the chat in the main room, or on the NASA Astrobiology Facebook page in the chat. Those questions will go to the queue for me to then ask Daniel during the show. Also, if you are on Twitter and using hashtag AskAstroBio, we'll catch those as well, and we can add those to the queue to ask your questions about everything Daniel's done in exoplanets and using observatories and using SOFIA, and in some of these next topics we're going to discuss. So for instance, Daniel, I'd love to talk about the NASA Frontier Development Lab, how you got involved with that in the first place, and maybe just to tell our audience what it is, and then what you've been doing these past few years with them.
Yeah, so NASA FDL, in short, or Frontier Development Lab, is a artificial intelligence machine learning incubator, where NASA defines certain challenges within their portfolio where they think machine learning could help to deal with these huge amounts of data. We mentioned all these planetary data, exoplanet spectra, whatever big data sets they have, Kepler data, test data, and then works together with partners from the industry like Google, NVIDIA, IBM, Intel, big players in the industry, define these challenges, come together for 8 weeks at the SETI Institute at NASA Ames, and then solve these challenges. And the unique thing is like not just this 8 weeks and this kind of like sprint or hackathon style. It's also that usually the teams for each challenge are half discipline scientists, so really people who know exoplanets or astrobiology or heliophysics, or also astronaut health was a topic, lunar mapping was a topic. So half of them are domain experts and the other half are computer scientists, artificial intelligence experts, and then they lock them up for 8 weeks basically at the SETI Institute and don't let them out before they solve these big challenges. So this is roughly how it works. And it's really a unique, quick turnaround, also in this, Silicon Valley mindset, have a lot of prototypes, fail quickly, and then just go with that one idea that you think can really get this moonshot done that some of these challenges are. And it's an amazing experience. Just because these interdisciplinary teams are just amazing. They invite like the smartest people from all over the world, from both domain science and computer science, and just to work with these folks for 8 weeks is just, a privilege really to have these amazing people around you for 8 weeks. And and it's a really novel way to do these kind of projects. I mean, it's still in the 3rd or 4th year, so there are obviously still a couple of things that we have to figure out how to do better, but it's really an amazing program, and I can really just recommend people, especially if you are a grad student or early career postdoc in one of our challenge areas, or in computer science. So really check the web page of NASA FDL. They are right now basically can put in applications for the next sprint this summer. Yeah.
And you've been a science mentor for FDL, helping these teams to advance their projects. I wonder how you feel about the future of using machine learning, of using artificial intelligence to solve some of our larger problems as a planet. I mean, we as astrobiologists, obviously, we have our own interest in trying to understand life and looking for signs of life on exoplanets and maybe even looking for messages from extraterrestrial life. But we also have many issues in our world, like global climate change, ocean acidification, deforestation, the rises in population causing a lot of urban issues, refugee crises. I wonder if you could speak to your own thoughts on what machine learning and artificial intelligence will be doing in the future to help us solve some of those problems.
So first of all, some of the FDL challenges actually were in these areas. So we had a flood prediction challenge last year, where the teams looked at satellite data, Earth observation data to predict where floods occur and when floods occur. There were challenges in FDL Europe who looked at settlements, undocumented settlements, how they evolve. We had challenges that looked at prediction of forest fires, for example. Some people were thinking about maybe doing earthquakes and other, hurricane prediction maybe to help that. So there's a lot of also more direct impact challenges. But I think even if it's not direct impact on climate change, if we, for example, study exoplanet atmospheres, there's so much exchange with people from the Earth atmosphere sciences that do climate science, to work against climate change. Also, you have to keep in mind, if we do this research, 90% of the people eventually move on out of academia into the industry, into jobs there. So if we teach someone in calculating the atmospheres of exoplanet, then he or she might be going to the industry or to some company that fights climate change after their education. So I don't think that it's exclusive at all, these topics.
Oh, yeah, interesting. And I think it's an important message too, is that our research on exoplanets and other worlds can come back home, and likewise it can go the other way too. People doing research here on various topics can then use those to help us understand other worlds. For instance, I help to manage this event every year in Utah from the Mars Society called the University Rover Challenge. And these undergraduate students who build these Mars rovers and bring them out to the desert and compete, it's always interesting because a lot of those students won't be working on Mars rovers in the future. They won't even be working in the aerospace sector. But it's cool to see them cut their teeth on an idea about how do we build a robot for Mars and then using that later in industry. So it's always interesting to see where those tie-ins kind of start coming together. So I'm very curious to hear a lot more about NASA FDL in the future and to see some of the cool projects coming out of it this summer and future summers as well. I want to change gears now just a little bit. I mentioned as the episode was starting that I'm now an associate of the Explainables, an organization that you actually are a founder of. And I'd love for you to chat a little bit about science communication and what has really driven you. You're a great speaker. You've given a lot of talks. I've shared some videos through our Twitter and Facebook these past few days of some of your talks for Astronomy on Tap and some of these things. You competed as a science communicator. I'd love for you to talk just for a little while about science communication and what it means to you.
Yeah, so the Explainables are actually sort of a baby of FameLab. So also like the event where the two of us met for the first time is, for some of you who might know it, I think it was organized also by the NASA Astrobiology Institute for a while. So it's a science communication competition. You get 3 minutes on stage. It's a little bit like American Idol for scientists. You get there, there's a jury, and there are winners and losers and local championships and national championships and then international championships. So this is where we met, I think, at RPI during an AppGradCon 10 years ago or something like that. And yes, I was always interested, not necessarily in the competition, but really in that communicating science, just going out. Like I think Carl Sagan said, if you're in love, you want to tell the world about it. And this is really, I just love my work and the research we are doing and the causes we are working for that I really want to get out with it. And I figured I'm, maybe like an average researcher or scientist, but I'm pretty good at the communication part. And then I just thought how I can, help others to get better at communication, how to maybe motivate others to design their own formats, to improve their own presentation skills. And it was really triggered by some of these workshops I did. So there were workshops, communication for scientists, but that were usually done by, coaches, people who don't really went through all the experiences that we had as, grad students, imposter syndrome, all the stuff that we had. If there's like an old or like a retired theater coach coaching scientists how to communicate, they might not have this connection. And this is kind of like this niche that we wanted to get in as explainable. So being communicating scientists that explain other nerds how to communicate better, basically. So especially in these interdisciplinary teams, as we have in astrobiology, you always have to find a common language with a geologist. So even beyond outreach, so often people, if they hear science communication, they think, yeah, that's your outreach talk, but it's really if you write a proposal, if you do policy making, even if, a geologist talks to an atmospheric physicist about exoplanets, it's science communication. So it's really everywhere where scientists communicate, we just try to help. Yeah, that's what the explainables do.
That's incredible. Yeah, I love that idea too about language and communication. I'm a member of many science communication groups, and one thing I've noticed a lot is that people seem to think that science communication is almost only synonymous with science journalism, which is only one very small branch of science communication. As you pointed out, even one scientist talking to a scientist from another discipline is communicating science, and we have to find that common language, which is one reason I think astrobiology is so great. Astrobiology teaches us to have a more common language across so many disciplines, so we can share some of these ideas. So I highly think our audience should go onto YouTube and find you and watch some of your talks. They're really awesome, totally worth a watch. I do want to remind the audience one more time, you can always ask questions on Twitter using hashtag AskAstrobio. You can ask questions on SegaNet.org and on the NASA Astrobiology Facebook page for Dr. Angerhausen. And we're going to chat just a little bit longer, and then I promise I'll open up to your questions here soon. So Daniel, one thing that you shared with us before we started advertising for this episode is that outside of your interest in science and science communication, you also play in a sport that I'll probably pronounce terribly wrong called sepak takraw.
Yeah, it's about right.
Close? All right, awesome.
I mean,
what is this? I went online and watched like one short video, and it looked pretty incredible.
Yeah, so it's a sport that is really popular in Southeast Asia. So especially Thailand, Malaysia. And the name actually is sepak means kicking in Malay language, and takraw means ball in Thai language. And it's like a volleyball game, so like volleyball, but with a net, with your feet. You play over a net. You got 3 players on each side. You can touch the ball 3 times on your side, and as soon as the ball touches the ground, it's a point for the other team. And the ball is like around this size of a fist, or a little bit bigger than a fist, and it's originally made from rattan, but now it's made from plastic, so it's pretty hard. Has like a little bit like a big ping pong ball in terms of consistency and how it gets reflected and stuff. Yeah, and I eventually ended up being on the German national team, but mostly because there are obviously not that many people playing in Germany. So it was whoever had enough money to travel to the World Cup was the national player. So I saw that when I was traveling Thailand about 20 years ago, and then went back to Cologne and was at the university. There was a group playing it, and then eventually we got invited to play in Thailand, and then we really started a little group in Europe, and now we have a European series for almost 20 years now. A lot of other teams from Europe, France, Switzerland also flying to these World Cups regularly. So yeah, that's the crazy sport that I'm doing, but not that often anymore, because I got a little bit old and my bones are not as flexible anymore as they were like 10 years ago. Yeah,
I was going to ask, because the videos I've watched, it reminds me, so I've been doing martial arts my entire life, and it reminds me of like growing up and doing Tang Soo Do and Taekwondo and watching all the trick kicking and trying to do jump spinning 360 roundhouse kicks and all kinds of weird things. Like some of the videos look very athletic, and some of these jump kicks these guys are doing. Have you done any of those, like jump over your head and snapping things?
I mean, I've like maybe like 5 or 10 years ago, I was able to do one of these, and maybe still get one of these kicks done. Not the somersault kick anymore, but yeah. I mean, it's actually, I mean, it's a mixture of, as you said, martial arts and volleyball and football. So, yeah, it's all about flexibility, and if you just stretch often enough, it's amazing how far you get. And it's just, I just also love to watch it. So people who watch football, like, you know, real football, soccer as you call it in the US, there's like, if there's a bicycle kick, like every 10th game, everyone freaks out. But in sepak takraw, every single ball basically has a bicycle kick or some sort of acrobatic kick in the end. So you don't have to wait for Ibrahimovic to do one of these goals once every 5 games. There's one every ball. So really highly recommend to check out sepak takraw on videos on YouTube and maybe even try the sport over.
That's great. Yeah, so hopefully the audience will go watch that. That'd be pretty cool. I'd love to actually give it a try too, even though, yeah, I'm also getting a little older now and starting to slow down a little bit with my jump kicks. I don't quite do as many of those anymore. Right. So before we open it up now, finally, to our audience questions, I wonder if you could go back to the very beginning and tell us about that bet that you lost that you mentioned that drove you towards studying exoplanets.
Yeah, so it was around that time when the first transiting exoplanet was detected, or the first transit of an exoplanet was detected. So by that time, I was, as I mentioned, at the end of my undergrad, I think, and had to find a topic or think about a topic. And I went on a road trip, I think, to Amsterdam with a couple of friends. And then one of my friends was like, oh, you know, they found this exoplanet via transit. So the light of the star got a bit fainter when the planet moved in front of it. And for some reason, I had missed that news. So it was maybe like a week after the press release, and I was busy other things. You know, at that age, you don't check the archive every day. So I had no idea that happened. So I was like, oh no, I would have heard about it. I know about radial velocity planets that were detected a couple of years before that, but I would have heard if there's a transit, let's bet. So I bet a box of beer that this transit is, he read something wrong. Also because that guy wasn't really an expert or physicist or anything. So he read it in some popular magazine, I guess. So I was like super convinced that I would have heard about this first transit observation. And actually that guy was right. And I had to give him a box of beer, a box of good German beer, but it also defined my career. So after that, I was like, oh, maybe I should then go and study transiting exoplanets. And here I am 20 years later, making that a whole career out of it. So yeah, that was it. Pretty cheap, right? Just 1 box of beer. So yeah, that was worth it.
So the take-home message, kids, is just because you lose, it's not bad. It might become the best part of your life. So we are going to open it now, Daniel, to our audience questions. Reminder for the audience one more time, to ask questions of Dr. Angerhausen, you can use hashtag AskAstrobio on Twitter or ask questions in the chat right now while you're watching. So our first question you actually mentioned already, and as I mentioned, it comes from Dr. Jim Pass, the CEO and president of the Astrosociology Research Institute, or ARI. He's a longtime friend of the show and often wants to consider the social sciences and their implications for our astrobiology research. So Dr. Pass says, hello, Dr. Angerhausen. I'd like to ask astrobiologists these questions that relates to increasing convergence between the 2 branches or cultures of science. So his question is, how can the social sciences and humanities increase their contributions to addressing astrobiology and SETI issues?
Mm-hmm. Yeah, so first of all, I think there's already a lot of great progress in this area. So for those who heard about the APSICON conference, there are sessions about astrosociology and how, you know, the humanities and astrobiology can work together more and better. So I think we are a community that maybe is a bit ahead of other communities in that regard. There are these obvious questions of, you know, how do we communicate if we find life? You know, what is a, you know, good protocol to inform people? Also, like the different levels of certainty we have was one thing we discussed in the past. If we are 80% sure we found life, if we are 90% sure, if we're 99% sure, how do we communicate that? And there's a lot of, you know, controversy how to communicate that, and people, you know, over exaggerate, and people and magazines, you know, clickbait and make headlines bigger than they are. So this is a big, also going back to this whole communication issue where social sciences come in. But then also, and that's what I already mentioned with the TMT discussion, there are real world problems. So as astronomers, as astrobiologists, we are not in some, isolated sphere. So we basically interact and have to, apparently need some help from social scientists in this case. So one other example is also big discussion at the moment is this whole Starlink. So people might have heard about this mega constellation of small satellites that SpaceX launched, which may really pollute our sky with more light sources, and then really make ground-based astronomical observations much more challenging. So this is also one thing I think where social sciences and humanity have to help us to get this communication going, to define as a society who owns space. Is it the astronomers? Is it the billionaires? Is it all of us? So I think these are really topics. If we go to the moon soon enough, who's owning the moon, who gets the mining rights? So these are really topics that we have to face right now and solve as a society. And this is where humanities hopefully help us.
It's a great point, yeah. And Starlink especially, that's a really good example of where those two can converge and actually work together, since we don't actually have any laws saying that you can't launch a constellation of tens of thousands of satellites and block out light from observatories right now. So it's a very good point, and well taken. Our next question comes from user Organism1974 on Twitter, AS1974, who's a longtime friend of the show as well. Hello. They ask if the recent discoveries of exoplanets in any way change the Drake equation in trying to understand whether or not there could be intelligent aliens out there communicating via radio.
Yes, so it definitely increased our understanding of the factors, or some of the factors in the Drake equation. So the equation obviously stays the same, but some of these factors, the fraction of stars that have planets. So with all these detections from Kepler, we know pretty good, or we have a pretty good idea, at least for the sample of Kepler stars, what fraction of stars do have planets. And we also slowly but surely get into that next term in this equation, which describes what fraction of these planets actually are in the right Goldilocks zone, habitable zone, in this right size and temperature area to be potentially suitable for life. So we are slowly but surely moving deeper and deeper from factor to factor over the next couple of decades. So and actually what's interesting is that Kepler was really designed to do that. So Kepler was designed to stare at one area of the sky, find all the planets that are in this area, that are in this sample of stars, to really do that kind of statistics. So TESS, the other mission that was recently launched, that does a similar job of finding it, really is just out there to find the closest one. Whereas Kepler was really also, in addition to that, a statistical mission. So a mission that really was supposed to get this eta-Earth, we call it, so the fraction of stars that have Earth-like planets. So so this mission was actually designed to exactly pin down this one factor in the Drake equation. So.
Awesome. So, it's good to remind our viewers, we've had, Kepler was looking at one very small place in the heavens, and the planets it discovered are all very close to the Earth, relatively. The same thing for TESS, the Transiting Exoplanet Survey Satellite. It's mostly looking for things that are fairly close by. I wonder, for you, as an astronomer who studies exoplanets, looking forward right now, we have some really amazing telescopes that are going to be launched here soon, like James Webb, these next generation of space telescopes. We have SOFIA doing observations. We have ground-based observations. I wonder, so if you could just tell us what you think the future is right now, maybe in the next 20 years or so, or 30 years, for exoplanet research.
So I think with the next missions like James Webb, and also Ariel is a mission that's built in Europe, which also does this spectroscopy and chemical analysis of exoplanet atmospheres, we first of all will get a much better idea about how planets form. So right now there's a lot of open questions. Maybe some remember before the first exoplanet was detected, everyone thought all the systems look like our solar system. This is, rocky planets inside and the gaseous planets are outside. And then everyone was surprised that we suddenly find these huge hot Jupiters, Jupiter-sized planets closer in than Mercury. And it's still not really explained how these, there's some ideas about migration and certain ways that they maybe get scattered within the system. But that's the first big thing that I think within the next 10 years, especially with James Webb, will be answered. The second one is this transition between what we call super Earth and mini Neptunes. So with the Kepler Space Telescope, actually one of the biggest the largest group of planets that we found are these intermediate-sized planets. So they are bigger than Earth and smaller than Neptune, of which we don't have any analog in our solar system. So there's this intermediate-sized, big group of planets which we don't have any idea if they are just, big rocks like Earth or small gas and ice giants. And this is, where this super Earth mini Neptune word comes from. And I think what we're also going to be pinning down, hopefully relatively soon, also with the Cheops telescope, for example, is this transition region. What are the densities? What is the transition region, at which radius or at which mass the planet becomes a gas giant? So these are the short-term questions. And then mid-term, we will probably get into this whole question of habitability. So how big does a rocky planet have to be to hold an atmosphere? What is the temperature or what are the areas where we might even be able to find water? But, and this might be a little bit of a bummer, but I think to really pin down biomarkers and get a definite detection of life. We might get lucky, so I'm not betting on this because I'm not good at betting apparently, but I think realistically also to do some sort of comparative exobiology, maybe even find a couple of candidates with life, we really need the next generation of telescopes, LUVA, HubX, LIFE. There are a couple of current mission designs that might fly in 20, 30 years. So that's my quick summary of my quick predictions, no bets for the next 30 years.
I love it. You don't want to lose bets in that area, but like you found out before, losing a bet's not the worst thing. Yeah. But that's a really, really interesting view on what's coming here in the future. Our next question comes from Facebook. I apologize to the user. I might mispronounce your name here. I believe the user's name is Kaike Roke. They want to know what are the difficulties of working with a telescope like SOFIA?
So first of all, people always ask me how it is to fly, and I'm always joking that it combines two of the most boring things. So all the observers, all the observational astronomers, after a while, it's just really boring to spend your night at a telescope and observing. So this is a really boring task. And then all of you who fly once in a while, do like 10-hour, 12-hour flights, know how boring that is. So first order observation flight with SOFIA just combines two very, very boring things. And then in the end, they become actually less boring. So obviously, SOFIA as a flying platform has a couple of different problems than a ground-based or space-based telescope. So first of all, it's the vibrations. So you can imagine, you all know these turbulences you get on a plane, and you still want to keep pointed at your star. So this is the main technical challenge that SOFIA had to solve, and they basically solved it with simple inertia. So the telescope is on one side, and on the other side of this bulkhead is a counterweight, so the instruments and some counterweight. So first order, the telescope is really swimming on a film of oil in this bulkhead. So you can really use your pinky and move the whole 16-ton telescope. It's amazing. So first order, actually, inertia keeps the telescope always pointed on the star. And there might also be videos on YouTube where you can see that, where the telescope moves and shakes during your flight, but it's actually the plane moving around the telescope while the telescope is pointing within 1 arc second on that target. And there's also passive and active damping, but first order is really inertia that keeps the telescope pointed. Another one of the problems that we encountered once was that the telescope cavity was behind the engine. So sometimes at very low elevations, you could actually see reflections of the exhaust stream in the telescope. So that was one of the technical difficulties we had. sometimes you just have to avoid weather. I mean, even if you're above the clouds, you still have to avoid certain other weather phenomena. Once we even had a government shutdown that kept us on the ground. So there are a variety of other problems that keep you from observing on SOFIA.
Yeah, a lot of technical and logistical issues, and it sounds like I have to find a video then of this telescope rocking while the plane is flying. I've always just had a fascination with how we can take such huge masses like that and allow them to move just using some very simple laws of physics in very smart ways. Our next question for you, Dr. Angerhausen, comes from SegNet from user Julia. She wants to know, what are your next scientific endeavors, and what advice do you have for the next generation of scientists in astrobiology?
So should I start with the second one? So I think a pretty smart. So if you want to do a career in astronomy, astrobiology, I think always wise idea is to connect yourself to missions. So look at the timetable when which missions scheduled at NASA, at the European Space Agency, that you can tie your career to. So this is usually a good move. For example, right now it might be a little bit too late to start working on James Webb because many people already know what they're going to do. It might be worth to look into the mission that flies after that. For example, the Dragonfly mission was just selected. So if I was an undergrad interested, that might be something to look into. So that's usually good advice to look at, at what age is that in my career is that mission going to fly. And there's also usually when there's a mission, there's money. I mean, in the end, you also have to look for funding. And this is maybe my first order tip is to look at the mission timelines and see how that fits your career. And then my personal next steps are, so I actually be moving institutes. So I'm right now at the Center for Space and Habitability at the University of Bern. But I'm moving to ETH in Zurich, so just 1 hour from here, so not far. And I'll be working actually on one of these super future missions. It's called LIFE, the Large Interferometer for Exoplanets. So it's, in short, it's a mission that combines a couple of telescopes in space. So it's like an array of space telescopes that will get us, hopefully, then that data that we need to find these biomarkers. So this is a mission, obviously, that's not going to fly tomorrow. So if we are lucky, it will be flying by the end of my career. So I didn't really take my last advice that nicely. So maybe, but if I'm a retired person somehow, see my mission fly, that would be nice too. So so that's one of my main projects. I have a couple of crazy SETI side projects. I have a machine learning project where we look for anomalies on the lunar surface. We are currently thinking about looking at some radio signals from Betelgeuse. So there are a couple of things. And I'm also expanding really on the science communication side. So I'm doing a lot of so-called science slams. So in Europe, it's a thing. I don't think it's pretty popular yet in the US. So if I say it's a science slam, people always think it's like a breakfast at Denny's or something. But it's actually like a poetry slam for scientists. So similar to Fame Lab or maybe some of Pint of Science or Astronomy on Tap. It's like a poetry slam for scientists. So 10-minute talks for the public audience in a bar setting or something like that. So I'm really even want to focus even more on the communicating side in the next year or two. Yeah, those are my plans, roughly.
That's awesome. That actually gives us a good segue into our next question as well. Our next question comes from user Mike on Facebook. Mike wants to know, when you're communicating science, what's your favorite age group to speak to, and who are the most fun to have in your audience?
I love to talk to everyone. I mean, I love to talk to my little 10-year-old nephew. I love to talk to senior citizens that sometimes come to these science slams. So I'm very agnostic when it comes to and I think it really every age group has their own nice thing about them. So kids ask the most creative questions sometimes, like elderly people really are into the details, so they can, talk to you about the details for hours. So I think I don't really have like a favorite group. What I do want to say though, and what is my advice for other science communicators, try to teach people how to think like a scientist and don't preach to people. So this is really, you can't emphasize that enough, especially in the times we live in right now. So really, science communication is not about standing on the stage and tell people what the truth is, but make people think like a scientist, ask them questions, put some riddles on the screen where they have to go through the thought process of a scientist. This is what I think is one of the important tasks we have as science communicators, to make people think like a scientist and not stand up there like demagogue to tell them, believe our story. So this is maybe, my biggest advice for other communicators, try to communicate with people, try to make them think like a scientist.
That's awesome. And it's an important reminder, too. I think sometimes even those of us who've trained in science communication can sometimes forget to ask important questions and allow the audience to discover for themselves. And sometimes you get lost a little bit in just sharing the story and not realizing that the fun of it is really going along on the journey in the story with the audience. So our next question here comes from Sam on SecondNet. Sam wants to know how you balance your time in doing research and in communicating science, how you find the time to do both.
Yeah, that's a really good question, and I'm also writing an open letter at the moment about this topic. So first of all, I'm really, really lucky since I had a fellowship for the past 3 years. So and a fellowship really allows you to basically do what I want. So this really allowed me to set a certain amount of my personal research time for communication, which is a luxury which not everyone in academia has. So if you're a grad student, you are 100%, paid by your advisor, and if they don't like communication, there's no way to do it. So I was really, really lucky and to have this fellowship to make that part of it. There was also people who told me, that senior scientists who told me I'm wasting my time, it's not good for my career. So I ignored that and just hope that it turns out good in the end. And I just enjoyed it too much. But it's really a problem. And one thing that really makes me mad at the moment, and what I want to write this open letter about, is that there actually is money for science communication. So there, it's not that there is no money, but it's usually not tied to the contracts of the actual researchers. So the actual scientists who communicate, that money just doesn't end up at these people. So there are big non-profits or organizations, foundations who organize science communicating events, maybe even, take an entrance fee, and, they pay the band that's playing on that event, and they pay the people who serve the food on there. But then the keynote speaker, who's a scientist, is supposed to do that for free. And I think this is really something like a thought process that we as a community have to change in people, that this is not something to take for granted. It's a bit, this example of, my friend is a designer, or can't you make a logo for me for free? It's good advertisement. Or doesn't your band want to play for free in my bar? So I think we have to have the same change of attitude towards communicating scientists, that people, pay you a decent honorary, or, pay more than just a train ticket to get there. So this is something, maybe we should have built a union of science communicators or something, and then to push our rights through. But this is something that I'm really, you see how I'm agitated, I guess. So this is really something that I want to change in the next years, that this get more appreciated on the academic side, but also in society.
That's awesome. I'd love to be a part of that myself. I've thought a lot about how science communicators who are speakers can become paid speakers in communicating science, because that's a huge realm right now, because you spend years studying how to speak well and how to share your knowledge. And so it's important, I think, that you have some reward for that. The same way, I don't think it's fair for us to ever think that an artist should sell their work for free or for nothing, when they've spent, years, decades, their lives learning their skill and learning their talent. So I love that point from you, Dr. Angerhausen. Thanks for sharing that.
That being said, also don't be shy to ask for it. So this is also what I tell. So that surprised me too. So once I started to actually ask people, in the beginning they assumed, he's doing it for free because that's what scientists do. But then when I told them, you see, I have to take a day off from my work, or this is a day that I can do, my other job, or, just pay me what I would earn in my other job. And then people realize, so often really it clicked with people. So sometimes it's even just, stepping out of yourself and saying, actually asking for something for it. So this is also something we on our, not just wait for the others to offer something, so really just also ask for it from our side.
Great point. So we were kind of short on time here, so I have one more question I'd like to ask for you, and then we're going to finish off our show here. This last question comes from Flora Dutra. You've spoken to this already a little bit, and so I'm curious to know your take on it. Flora is a doctoral student in anthropology. They'd like to write their thesis on the approach of astrobiology to the humanities, and they wonder from you if you think that's possible.
First order, it's always good to connect two new things or to make a connection astrobiology that's off the beaten path. I think it's then important to be not too general, so really to focus on one or two problems, maybe some of them that we mentioned, or maybe there's similar problems in more anthropological topics within astrobiology. So I think especially at that level, when you graduate when you're about to graduate, when you do your PhD, this is really the time in your career where you're the most focused. So career is like an hourglass. So you're the most focused when you write your PhD, and then after that you get broader again. So I think you start with a broad idea. I want to be in science, and I want to be in astrobiology, and I want to be in field geology, and then you solve this one topic, and then after that you diverge again, and maybe help building a code for an exoplanet atmosphere, or build a mission. But I think at the point of view, and this is a general tip, at the point of your PhD, really focus on one particular question, if that helps at all.
Yeah, I hope that helps, Flora. So before we leave, we do want to mention, so today is the day that NASA is opening up the voting for the Name the Rover competition. So for those who don't know, the Mars 2020 rover has been called Mars 2020 for some time now, and now we're going to give it a real name, a good, proper name, like we had Spirit and Opportunity and Curiosity. And so I was one of the first round judges in the Name the Rover competition, which is run through Future Engineers, a nonprofit, as well as through NASA. And I was blown away by the kindergarten through 12th grade students who submitted their essays and their ideas for names. We now have a list of 155 names. Our director and producer, Mike, is going to bring up on the screen a link to how to go find all of those names right now in the list. And once the voting is open, that'll tell you where to vote as well. So for you, Dr. Angerhausen, I'm curious, what would you choose as a name for the next Mars rover? And maybe even better for you would be, what would you choose for the name for the next large telescope?
So when we started to talk about the show, you told me I shouldn't say Rover make Rover face. That would be my first guess, Rover make Rover face. No, I really think like something like humanity or humankind. So really, that expresses that this rover is kind of like an ambassador or someone we as humanity sent there. So some name that goes into this direction. I would love that. Maybe someone came up with some smarter way to express that, but something that really shows that this is someone we sent there. So and for the next big telescope, maybe they should stop calling them after old men, and maybe it's time to name a telescope after a female, or maybe just stop naming them after people at all and just call them like the Mars rovers. So sometimes acronyms are pretty neat too. So I like acronyms. So yeah.
Awesome. That's great. And I'm being told right now by Mike that the voting is open for everyone watching. So you actually can go online right now and vote to name the next Mars rover. So you can get out there and vote. There's 1 week left to vote. I'm curious myself after the show. I'm going to go check and see what the actual final options are for voting now, finally. So Dr. Daniel Angerhausen, thank you so much for joining us for Ask an Astrobiology. It's been great having you on the show.
Yeah, thanks. It was a pleasure and an honor to be on the show. Thanks.
Yes, thank you. And to our audience, as always, thank you so much for joining us for Ask an Astrobiologist. Remember, you can always follow our show online. Always ask questions using hashtag AskAstrobio on Twitter, and we'll announce our next episode very soon. So until then, we'll see you around, and remember, stay curious.